Okay, so again, we have type 1 error. So this can be thought of as the false positive, where the truth is the null hypothesis is true. Our decision is to reject the null hypothesis. And then the type 2 error would be the false negative, where the truth is the null is false, and our decision is do not reject the null. Okay, so this is how type 1 error and type 2 error work. What we have is a few things going along with that. Alpha is the probability of a type 1 error, and beta is the probability of type 2 error. Stay healthy, everybody. You don't want to get sick this week. It's like the worst week to get, not that there's ever a good time to be sick, but finals week is not a fun time to get sick, okay? So get plenty of rest. It's I'm a believer that you perform better if you're well rested prior to a final than trying to like cram nonsense into your head, okay? Useful nonsense of statistics, right? Okay. All right, so we got type 1 error, type 2 error. Let me try to think what a good question could be regarding type 1 and type 2 error. Oh man, I'm having trouble coming up with some questions here. Okay, all right. How's this? Okay, so you perform a hypothesis test to see if the proportion of men who wear glasses is different from the proportion of women who wear glasses. Okay, so just think about what the what your null and alternative hypotheses would be. Okay, and then now let's decide. Okay, so if we conclude that the proportions, or maybe I shouldn't sit right out. Okay, if we conclude that we do not have evidence that the proportions are different, and in reality, they are different, then this is ... Okay, so your answer choices, I guess we'll make a clicker question out of this. answer choices will be correct decision. B will be type 1 error. And C will be type 2 error. Okay, so this is the setup of the problem. The question is, if we conclude that we do not have evidence that the proportions are different, and in reality they are different, then this is what? So we're performing a hypothesis test to see if the proportion of men who wear glasses is different from the proportion of women who wear glasses. Okay, so it's always, when you're trying to think of what is type 1 error and what's type 2 error, always think of in your head, what is the null hypothesis and what is the alternative hypothesis, okay? And what's helpful is to remember that the null hypothesis always has an equal sign, okay? Okay, do we all get our clicks in? I'm going to click stop here in a second. Okay, and our answer choice is indeed choice C. Okay, all right. Let's review this. Okay, so we're going to perform a hypothesis test to see if the proportion of men who wear glasses is different from the proportion of women who wear glasses. So our null hypothesis will be that the proportion for the men is equal to the proportion for the women. Okay, and our alternative will then be is that they are different. Okay, so what we concluded that we do not have evidence that the proportions are different, okay? So that means our conclusion is that we don't have evidence that the proportions are different. So we're going to do not reject the null hypothesis. This is our conclusion. And in reality, they are different. So the truth is that the null hypothesis is false, because the null hypothesis states that they are the same, and the truth is that they are different, so the null is false. So we didn't reject, and yet this is false, so this would be type 2 error. Okay. Do we have questions on this? Okay, and so, you know, what the type 1 error would be, the type 1 error would be, we conclude that the proportions are different okay, and yet in reality they are the same. And that would be a type 1 error. Okay. Other topics or questions? Have we taken a look at the practice final? Yes, a little bit, not yet? Yeah, question?
Oh yeah, just on the topic.
Okay.
Can you go over like scenarios where you have to decide which condition is like not met for the central?
Okay, sure. Yeah, we'll talk about checking the conditions for central limit theorem, okay? So we haven't really emphasized this in our class, but the truth is we should check the conditions to use the central limit theorem every time we do statistical inference, okay? The problem is when you write an exam, it's hard to ask questions if part of the problem is like you check conditions and then you find out that they're not met, then technically you're supposed to stop, right? But you know, how do you ask questions about this without, I don't know, trying to lead you into a trap where I'm like, you know, give me the p-value, but oh, trick question, the p-value is not valid because the conditions weren't met. So, so what I've done is I've separated it out, right? So just at the beginning of the test, there's going to be like a few questions where you check the conditions and you say, you know, they're met or they're not met. And then all of the other things where I'm asking you to give me a p-value or give me a conclusion, it's safe to assume that the conditions are met to use inference there, okay? So I'm not going to be trying to set you up into little traps there. Okay, so the conditions are, we have the random/independent condition. Whoops. Okay. I always forget what order I put these things in, okay? We have the big population condition. And we have the large sample condition. All right, so a lot of times students forget or just mix up which one's the big population and which one's the large sample condition, okay? So basically, big population means, is the population big enough? Okay? And then large sample condition, is the sample large enough? I mean, it seems silly, but okay? This is how we're going to go, okay? So when we say, is the population big enough, okay, the thing here is you're going to have to check the size of the population versus the size of the sample, okay? Check population size versus sample size. Okay? And is the sample large enough? This is just either, you know, check the sample size, and in particular, successes and failures. Okay? So there's no mention of checking the population for the large sample condition. Okay? So if part of your check for the large sample condition involves the population, you're probably mixing something up here, okay? So the big population condition is the only one where the size of the population actually plays a part, okay? So, you know, to check the big population condition, what we want is, what we want is the population to be at least 10 times the sample, okay? Now, sometimes the population is not clearly defined in the question. It'll say something like, you're interested in knowing the proportion of, I don't know, the proportion of people who have some disease, or the proportion of whatever, okay? And in that case, if it's like proportion of people who have a disease, the population would be everybody who could possibly be counted as potentially having the disease, which would be, you know, 7 billion people, or however many people there are, okay? So the big population here, you know, sometimes the population is defined. Population size is defined, okay? It might say you're like going to draw a sample from a school where the school has 800 students, okay? Okay, so, you know, example, a school. Okay, and so in this case, if the population size is defined, then, and it says the school has 800 students, then you know your sample can't be more than 80, okay? And then otherwise, the population, sometimes the population is not defined. Population size is not defined. So I think, you know, on one of the tests, we talked about like drawing M&Ms from the store or something like that, okay? And so the population in that case would be like all the M&Ms out there, all right? And generally, if the population size is not defined, this generally means your population is quite large, okay? You know, generally safe to assume that the population is large. Okay, like in the order of thousands or millions, where you're not going to have to worry about, is my population big enough? Okay, for the large sample condition, it's technically different for proportions as it is for means, okay? So what we've dealt with was for proportions, we want to make sure that we have at least 10 successes and at least 10 failures. Both the number of successes and failures have to be over 10. Okay, so at least 10 successes and at least 10 failures. If the counts aren't given, then we would do n times p is greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. I saw a hand up. Oh, that was your question? Okay. So if the counts aren't given, you know, you can check to see, make sure that we're going to expect at least 10 successes and 10 failures. Yes? What's the difference between a capital P and a lowercase p? I'm trying to think where I'm using a capital P. Generally, the capital P will be like capital P of you know, like x equal to 5 or something. This is like a probability, but as far as, you know, our hypothesis tests go, we're generally almost always using little p's. Okay, little p's for population proportions and things like. I know we've got so many p's showing up in this class. You got the p for the proportions, and then you got p hats for your sample proportions, and then you got p hat overall when you get, and then p values, and that's whatever. Okay. So yeah, I apologize that we like to use the same letters over again. Okay, so that's what we've got. And then the, you know, random independent condition, you just want to make sure somewhere in there it says the sample was obtained randomly. This is we gloss over this, but the truth is in real life statistics, this condition is rarely met. And so you can always question in your head, well, was this a random sample? Can I trust the answers that I get here? Okay. So anytime somebody does a survey on the internet, okay, I don't trust the results, okay? Just because I'm like, that's not a random sample, okay? People vote on whatever. Do people even vote on American Idol anymore? Is that thing still going? Like, not a random sample, right? Whatever else, any of these phone in your votes. They're not random, not necessarily representative. So, whatever. Okay. This is what we got. Do we want examples, or does this kind of clear things up here regarding?
Can you give like one?
Yeah. Okay, so let's try something out here. Okay, so we'll say researchers wish to study the effectiveness of a drug. Okay, so they randomly select people with, I don't know, type 1 diabetes. I don't know how to spell diabetes. Okay. All right, and so their sample has 100 volunteers. Okay. They randomly split into 2 groups. Of 50, okay. One group gets placebo. The other group gets the drug. Okay? In the placebo group, 10% show improvement. Okay, in drug group, 20% show improvement. Okay, can we perform a hypothesis test to see if there's a difference between proportions? So, our conditions, we have to see, random and independent, big population, and large sample. Okay. All right. Let's turn this into a question here. All right, so your choices are either the random independent is violated, big population is violated, large sample is violated, or no conditions are violated, okay? Okay, I'm seeing our answers come in. Hey, I made this one a little bit harder, but yeah, we'll see. See how we're doing. Okay. All right, just a few more seconds to get your clicks in. Is this everybody? I think this is everybody. Here we go. Okay, and our answer, the correct answer, is indeed C. Okay, so let's go through and see why or why not these are not met. Okay, so random and independent, they were randomly selected and they were randomly split into groups. Okay, so this thing is met. Okay, big population. What is our population here? It would be all people with type 1 diabetes. Okay, so the population is all people with type 1 diabetes. Now, we don't know how many people who have type 1 diabetes, but our sample has 100 people, okay? 100 people total. Is it safe to say that there's more than 10 times that, more than 1,000 people with type 1 diabetes? Yeah, okay. So, you know, this is going to be large. Over 1,000. Over 10 times 100. So this one's going to be met. Okay? Our large sample condition, okay, so now we have two groups, okay? We got group 1, the placebo group, and we have group 2, the one with the drug, okay? So in group 1, how many successes do we have? Okay, so group 1 we have 50 people, right? So N1 is equal to 50, and then in group 2 we also have 50. Okay, so our number of successes is going to be 50 times our P, which is 0.1. So I have 5 successes here. As far as the number of failures go, it's going to be 50 times 1 minus 0.1, or 0.9, and I get 45. Okay, so this number is not bigger than 10. Okay, we can check group 2. It doesn't really matter. Once we see that group 1 is violated, it doesn't work. Okay, but the successes here for group 2 will be 50 times 0.2. This is equal to 10, so we're okay. And then the failures will be 50 times 0.8, which is 40. And that's bigger than 10. That's okay. 45 is bigger than 10, but 5 is not, okay? So this is not bigger than 10. So that's why the large sample condition is violated. All right, question? Okay, different topic. Okay, okay. So before we go on to another topic, I just want to make sure this does that work out? Yeah. Okay. And this is probably about as complicated as it's going to get. Okay, where you have 2 samples and you want to check the number of successes for sample 1 and the number of successes and failures for sample 2. Okay. Conceptually, talk about the t distribution. Okay, so going from the t-score to a p-value?
Yeah, like what is that?
How are you? Okay, sorry. Let me just make sure I understand your question. You want to know how to use the t table, or you want to understand like the theoretical workings of the t distribution here? Okay. Yeah. I don't think we need to know the theoretic workings of the t distribution. Okay. You can just think of it as a relaxed version of the normal distribution. It's, but yeah, don't sweat it. Okay. Just if you're okay with going from a test statistic t to getting a p-value, then you're okay. Okay. Should we try that out, or are we feeling okay with that? Yeah. Question.
For like when you get your value for doing like a test and it's a range, if it's a two-tailed test, do you multiply the range by 2?
Okay, so this is a good question. Okay, so the question is, you know, when we get look something up in the t-table, we're going to get a range. Okay, the range applies to the tail area, and what if it's a two-tailed test and whatnot? Okay, so this is for hypothesis tests for means. Okay, this is the only time you use the t-table to get a p-value. Okay, hypothesis tests for means. So there's two scenarios, right? You got one sample and you have two samples. When you're doing hypothesis tests for means, then you look up your t in the t-table to get a p-value. All right, so let's cover a few scenarios. Okay, so scenario 1. Okay, the alternative hypothesis, has a not equal sign. Okay, you do your math. Dot 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 dot. You get your t is equal to 2.1, and you've got degrees of freedom equal to 9. Okay? So you look this up. Or here, actually, let's say t is equal to negative 2.1. Okay? Because this will make things a little more interesting. Okay? So t is equal to negative 2.1. Degrees of freedom is equal to 9. Okay? So what we're going to do is we're going to look up t equal to positive 2.1, okay? But because we've flipped the sign from the negative to the positive, this means that the numbers at the top now correspond to the left tail area, okay? So because we changed signs on t, the column headings are left tail probabilities, okay? So, oops, that's the other class. Okay, so we're going to go to 9. We look up 2.1. 2.1 is in between 1.833 and 2.262. So our column headings are between 0.05 and 0.025, okay? So we got, I already forgot. What is it? 1.833 corresponds to 0.050, and 2.262 corresponds to 0.025. 2.1 fits in between here. Keep in mind, because we flipped the signs, this is now our left tail probabilities. Okay? And so our tail is between 0.025 and 0.050. Okay? Because our alternative has a not equal sign, okay, we will double our tail area to get our p-value. Okay, and so what we have is our tail is between 0.025 and 0.05. Okay, so sometimes students get a little bit mixed up. You can just drop off any trailing zeros after the decimal. Okay, so 0.050 is the same as 0.05. Okay, so the tail is between this. So if we double that, then that means our p-value is between 0.025 times 2 is going to be 0.05, and 0.05 times 2 is 0.1. Okay, so another way to write this is 0.05 is less than our p-value, less than 0.1. And that's what we have. Yeah, question?
When your degrees of freedom, like let's say it's like 61 or something, it's not on the table, but you go to the nearest value? Or?
So I recommend always rounding down. Now, other textbooks might say different things, but the way I was taught, you always round down to stay on the safe side, okay? So you know, if you have 89, like 99 degrees of freedom, okay? If you have 99 degrees of freedom, don't use 100, use 80, okay? You just round down, okay? Other texts might say use 100, okay? But in our class, we'll round out. I don't think on the exam, I don't think there's going to be like I don't think I have any questions where if you accidentally used 100 rather than 80 or something, it would give you a different answer. Okay, I don't. It would really only make a difference if your answer is like right kind of in here, like 1.987 or something, and then it makes a difference whether you use the 100 or the 80 degrees of freedom. But I don't think I have anything like that, so you should be okay. All right. Let me just talk a little bit more about kind of getting our hypothesis test stuff. Okay. So we will say we've got the same scenario here. Okay. Except this time under scenario 2. Oops. Okay, under scenario 2, the alternative hypothesis has a less than sign, okay? So when HA has a less than sign, we expect T to be negative. And conversely, when the alternative has a greater than sign, we expect T to be positive, okay? So we expect T to be negative, and when HA has a less than sign, our p-value is equal to the left tail area, okay, or area to the left of T, okay? So this is perfect because, you know, we're going to look up positive 2.1 and knowing that our column headings now are equal to our left tail area, okay? Because anytime you switch the sign from a negative to a positive, you know that the column headings no longer correspond to the right tail area, but the left tail area, okay? And so because of that, you know, you look up, what was it, 1.833 and 2.262, I think those were the numbers, okay? This corresponds to 0.05 and 0.025, and we have 2.1 is in between here. We're going to get our left tail is between 0.025 and 0.05, okay? And because our p-value is equal to the left tail, then that means our p-value is between 0.025 and 0.05. Okay. Now this shouldn't happen, but if the alternative had a greater than sign and you got a t negative, then you have to get the area to the right, and you would do 1 minus this, and you would get something between 0.95 and 0.975. That shouldn't happen, okay? It means like your alternative hypothesis was probably set up incorrectly. But it could happen, okay? If you set up your alternative in a way that doesn't make sense, or maybe your data just doesn't match what you were hypothesizing, that could happen, okay? And then, you know, so effectively, you just look up positive 2.1, and then you get the column headings and know that that's your p-value when you get less than and a negative. Yeah.
So would it always be either an equal sign or a like greater than sign?
What's that?
So for the alternate hypothesis, would it always be like an equal sign or a greater than sign?
Yeah, the alternative will never have an equal sign in it. The alternative will either.
Yeah.
So that. Whoops. So the only other possible scenario is will be that the alternative has a greater than sign. Okay, so the alternative will always have not equal or greater than or less than. Okay, these are one tail, and this would be the two tail test. Okay, so if the alternative has a greater than sign, okay, we expect t to be positive. Okay, and then and our p-value is equal to the area, right tail area, or right tail probability, whatever we call it. Okay, and so in this case, if t is equal to positive 2.1, then you just look it up, and you have 1.833 and 2.262, and indeed, you get your right tail is between .025 and 0.05, which means your p-value is between 0.025 and 0.005. Okay. I know it feels like I'm always being redundant when I'm always writing like the tail is between this and then our p-value is between this, okay? But the reason why I always kind of write the same thing twice is because when it's a one-tail test, you take, you know, your tail area and then you use whether it's the right or the left area, okay? When it's a two-tail test, you'd say your right tail is between this and this, but it's two tails, so we double that, so our p-value is going to be between the other numbers when you double them. Okay. All right. I'm confident in you guys. You guys have always made me proud with the test 1, test 2, and your quizzes. So I know you guys will do great on the final exam. So you know, good luck studying, but don't have too much stress. Well, thank you. That's very, very kind. So anyway. Good luck. We'll see you guys on Wednesday, and good luck on all of your other finals and all of your other classes. Enjoy yourselves.